This is the final chapter for Unit 2. Looking at an exam on Wednesday, but this chapter is titled Energy and Metabolism. So the first section is the flow of energy in living systems. I want to talk about the difference between kinetic and potential energy. This is Physical Science 9 review. Identify the source of energy for the biosphere, and then revisit redox reactions, aka oil rig. So, chapter 6, we're going to get into the laws of thermodynamics. And so, this is a branch of chemistry that deals with energy changes. And there are 4 laws. I know there are 3, but then we have a 0th law. But we're going to go through these laws, the first and the second law, in detail here, looking at how energy is conserved, but how it can be converted to different forms, and then how do energies flow. So cells are governed by the laws of the physics and chemistry, and that's why this chapter is thrown into this unit. Okay, so energy can take many forms, and the definition of energy in any science textbook is really the capacity or the ability to do work. And there are 2 states. You can have kinetic energy or potential energy. Kinetic energy is the energy of motion. Anything that moves is basically like kinetic energy, an example of it. Whereas with potential energy, it has the potential or the ability to do work. It's stored energy. So here we have a car, it's going up a hill, and it does require energy to get up here. So we're using energy, it's moving, there's kinetic energy. But at the top of the hill for a split second, you have potential energy because this potential energy can be converted back to kinetic energy. So you can kind of see that there's energy being transferred from one form to another. There are many, many different forms of energy. So kinetic energy is movement, okay, motion. Sound is a form of kinetic energy. Thermal, because temperature is really just looking at the average particle movement. Wind, light, electrical, those are all kinetic forms of energy. Whereas with potential, it could be chemical, breaking of bonds. Gravitational, holding a ball up high and then letting it go or rolling it down a slide. Elastic, okay, like the tennis racket strings or springs. Electrical, I know electrical is both over here because it can be both, and nuclear. So energy can take many forms: mechanical, heat, sound, electric current, light, radioactive radiation. And it can be measured in many ways, but the most convenient for us is really heat. And if we look at the laws of thermodynamics means heat changes. So how we measure heat in biology is with a kilocalorie or a kilocal, where 1 kilocalorie equals 100 calories. This is different from the calories that we eat. The calories that we eat is actually a kilocal. It's written out with a capital C-A-L. Okay, so I just wanted to. They are related, but they're not the same thing. So 1,000 calories is 1 calorie in a food, like a Nutri-Grain bar or something. But anyways, a calorie is the heat required to raise that temperature of a gram of water 1 degree Celsius. So, yeah. Moving on to another unit that's related to heat and energy, joules. Joule is 0.239 cals. Now, the ultimate source of energy for us on Earth and for all living things is the sun. It's estimated that the sun provides Earth 13 times 10 to the 23rd calories per year, or 40 million billion calories per second. We rely on photosynthetic organisms to capture this energy. And if you don't know what photosynthesis is, we take water, CO2, and sunlight, and we make sugars and oxygen. So we're basically taking carbon from this inorganic form, CO2, and converted it into an organic form, sugar, and storing energy in those covalent bonds of atoms and sugar. And when we store the energy in covalent bonds of atoms and sugar, what we're doing is it's storing this energy as potential energy, okay, the ability to do work. Now, when you break these bonds, energy will be released. But I just want to point out that it requires the same amount of energy to form those bonds. So if it takes 98.9 kilocals to break 1 mole of CH bonds, it's going to take 98.8 kilocals to form a mole of CH bonds. Now, redox reactions or oxidation reduction reactions means that electrons are going to be transferred when bonds are made or broken. And remember our little saying, oil rig. oxidation and loss of electron, reduction and gain of reduction and gain of electron. So when an item gets reduced, as you can see here, okay, no, this guy's getting reduced, okay, so y is reduced by x, it becomes more negative, x is oxidized by y, it becomes more positive. When items get reduced, they actually have a higher energy level because they gained that electron. Okay. So some review questions. A covalent bond between two atoms represents what kind of energy? That is B, potential energy. During a redox reaction, the molecule that gains an electron, sorry, some typos here. The molecule that gains an electron has been what? So oil rig, we're looking for the gain, so it's going to be the rig, so it's going to be reduced, so it's either going to be A or C. And now that we have gained an electron, we're going to be at a higher energy level. So your answer is A. So differentiate between kinetic and potential. This is movement. This is like stored energy. The source of energy for the biosphere is the sun. And the nature of redox reaction, oxidation and loss, reduction and gain. And when you gain electrons, you have a higher energy level. When you lose electrons, you have a lower energy level. Okay, let's focus on the laws of thermodynamics. So I'm going to go through the laws of thermodynamics and talk a little bit about free energy, and then throw in enzymes, so reactions that occur in living organisms. Okay, so the first law of thermodynamics is that energy cannot be created or destroyed. It can only change from one form to another. So the one thing I need you to realize is that the total amount of energy in our universe remains constant. Okay, it doesn't go up, it doesn't go down. Whatever there was when the Big Bang happened, like this is it. This is all the energy that we will ever have. And so in any living organism, that chemical potential energy stored in molecules can be shifted to other molecules, or it could be stored in different chemical bonds, as well as be converted to other forms. So a nice picture to represent the first law of thermodynamics is this is your energy before the chemical reaction, this is your energy after, and you can see that it can be transformed into different forms. During each conversion, some of the energy is lost to the environment as heat, and this is a huge problem, especially in engineering, like friction, like machines. There's always this loss of energy through heat, and so when they make machines, they try to make it more efficient by reducing friction or reducing heat loss. I just read an article about superconductors and how superconductors produce electricity without any resistance. So like when electricity travels through wire, there's loss of energy as heat, or as it's traveling through the wire. And these superconductors, what they do is they try to lower the temperature so you don't lose energy as heat. And I just read this article saying that they made one that occurs at 15 degrees Celsius. However, you have to increase the pressure. It's like 2.3 million times Earth's pressure. So it's not really useful at the moment, but it does have possible applications that we could build off of. So anyways, back to heat. So heat is the measure of the random motion of molecules, and we can harness it to do work only when there is a heat gradient. So moving from high to low. Now our cells are really small to maintain significant internal temperature differences, so heat cannot do work for cells. So that's a bummer. So instead, heat, will escape from these chemical reactions and dissipate as heat, and that's why cells are usually made up of water to help absorb that heat and keep the cells at a constant temperature so it can do its job properly. Okay, so that's the first law, energy transformation, basically. So energy cannot be created or destroyed. It only changes from one form to another. Now, the second law looks at how some of that energy is lost as disorder increases. Okay, so I got to talk a little bit about entropy, disorder in the universe. It's continuously increasing. So your book describes the second law as the time arrow law, which means that energy transformation goes from spontaneously to convert matter from a more ordered to a less stable to a less ordered. Entropy is basically like you clean your room, right? It requires energy to clean your room, and then give your room a week and it's going to be a disaster. Or like my classroom. Like I can come in on the weekends and clean it, but then by the end of the week, entropy has increased because it takes work to keep things organized. So put simply, disorder is more likely than order. So if you see a column of bricks, it's more likely that they will tumble over than a pile of bricks that will just spontaneously arrange themselves to form the column. So when our universe formed, it had all the potential energy it will ever have, and it has become progressively more disordered ever since. So entropy increases as time increases. So some diagrams I think that will probably help solidify what really entropy is. So here we have a bricks, and you can see that the bricks are laid in an orderly way. And what this diagram is saying is that it's improbable for these bricks to fall from the air and to align themselves this way. This is a more probable way for the bricks to fall. So entropy right here. Or looking at a jar here of two different molecules, green and yellow, highly ordered, solid, low probability of this actually happening because entropy always increases, and instead you'll probably get a more disordered liquid. Okay, so like solid tends to be more highly ordered because you're putting energy into it, but then when it melts and turns into a liquid, now you have chaos, or not chaos, but disorder, which is entropy. So here's a block of ice. Entropy is denoted by the letter S. As it increases, you get a puddle of water, but then as it freezes, your entropy decreases and the molecules arrange themselves in an ordered way and you get a solid. This is a comic strip. Man, woman, I just feel that our relationship's entropy has increased. Ouch. Okay, so chemical reactions can be predicted based on the changes in the free energies. So it takes energy to break chemical bonds in atoms. So if it takes energy, our heat energy is going to increase, and as we increase our heat energy, it makes the atoms pull apart a lot easier to break those bonds. So chemical bonding, when you form bonds, reduces disorder. Heat increases that disorder. And so I'm going to throw in another vocab term here, free energy. Free energy is the energy available to do work in any system. Basically, it's the net energy after you break or form bonds. It's what's ever left. So a diagram showing the second law of thermodynamics. Here's our energy before, and now we have heat, or heat. So we can't use it. So this is the unusable energy after it's been transferred to a different form, and this is all we have left that we can use. So it's kind of like, I think when we talked about ecology with the food chain, you know, if I eat 1,000 joules of spinach, I can't use the 1,000 joules. I can only use like 10% of that, so 100 joules. And then if a cougar eats me, then it only gets 10% of the available energy left. But you can see that over time, the free energy does, decrease with each transformation. Okay, so free energy, which is the energy, that's left, the net energy after breaking and forming bonds, is actually called Gibbs energy, denoted by capital G. And G is equal to the energy contained in a molecule's chemical bonds, also known as enthalpy. So how do you find G? Well, there's this equation here. Enthalpy minus temperature times entropy gives you your free energy. So H is enthalpy minus the energy unavailable because of disorder, S, times the absolute temperature in Kelvin. So let's take a look at each one of these variables, H, S, and T. Okay, so delta G, okay, that's your free energy. I also like to call it your available energy. I really hate the word free because it's not free. It's just what's ever left over. So we're just going to call it available energy here. Spontaneous reaction means that if you give it a push, it will go on its own and release energy. Okay, so here I have these solutes with the semi-permeable membrane, and if you give it enough time, it will distribute and reach equilibrium. Here I have these cherry bombs. Okay, they're probably not going to release on their own. They're probably going to need a push, like a little push. And then once you light that cherry bomb, then it's going to release its own energy. So just need a little bit of energy to start this. Like tennis ball, you just need a little push. This was probably a spontaneous reaction. But H is enthalpy. Okay, so enthalpy, remember? Actually, we haven't really discussed what enthalpy is. But let's just check out this system. Here we have a slide with a tennis ball. What's going to happen to the total energy, H? That's what enthalpy is. So potential energy is greater at the top than at the bottom. So if we start this reaction before and after, our enthalpy is going to decrease. So you can see my big H becomes a smaller h, so H decreases. And so the potential energy is basically the bonds in living organisms that once a chemical reaction starts to break them, then the potential energy will decrease. Let's take a look at entropy, S. Remember, entropy is like disorder or randomness. So here I have this picture of the semi-permeable membrane, and we're looking at diffusion, moving from high concentration to low concentration. If we remove the barrier, what happens? Well, the molecules are going to spread out and become more random, and as a result, entropy is going to increase, right? So we're going to get even more disorder. And so you can see here, my S, my entropy, gets bigger and bigger over time. I had to plug in my laptop. I'm going to lose power here. That's embarrassing. Okay. All right, so let's take a look at a cherry bomb right here, okay? Does it explode on your desk? If I were to plop a cherry bomb at everybody's desk, is it going to spontaneously explode? No. But if we built a fire or struck a match, we increase temperature. Temperature increases the chances that it will more likely explode. Or if you leave it in a hot car, more likely to explode. So chemical reactions break bonds in reactants and can form new ones in products. So reactions can basically produce changes in our free energy. What that means is, here's our equation, and the triangle means delta or change in, okay? So if you factor in your enthalpy, your temperature, and your entropy, and you end up with a G that's positive, well, that means that the products of your reactants have more free energy than the reactants. That the bond energy H is higher, or the disorder S is lower. And as a result, this is going to be an endergonic reaction, which means that it cannot proceed spontaneously. You need the input of energy. So all it's saying, if you were to stick in like imaginary numbers here, like let's just say T and S are 1, right? And I have H as 2, okay? So 2 minus 1 times 1 is 1. 2 minus 1 is 1. So this is positive. So that means that my H was higher, or maybe my S was like really, really low. So if I left this as like 1 and this was like 0.5, you know, I still end up with a positive G. When your G is negative, that means your products, your end result of your chemical reaction, have less energy than the reactants. So as a result, your H is probably going to be lower, like a low number, maybe like a 1, and then these guys are 2. Like 2 times 2 is 4. 1 minus 4 is a negative 3, so you end up with a minus 3 for your delta G, or both, yeah. So it can proceed spontaneously if it's different, okay? Oh, sorry. So this reaction, yeah, so this will be a spontaneous reaction, and as a result, you end up with an exergonic. It's going to release this excess of free energy, exergonic. So in summary here, when G is negative, okay, it's a spontaneous reaction, it's exergonic. A great example is cellular respiration. Okay, when G is greater than 0, man, I have a typo. It's not spontaneous, it is endergonic. A great example would be photosynthesis. And if you ever end up with a delta G that's 0, then we just call it equilibrium. So another summary. This one's looking at equilibrium. You know what, I'm just going to skip this slide because I think this slide does a great job just saying, how do you get a positive G or a negative G? Okay, now chemical reactions are reversible, and it just means that if it's exergonic when you go in one direction, when you go in the opposite direction, it's going to be the opposite. So it's going to be endergonic in reverse. And then when you reach delta G is 0, then you have equilibrium. Okay. So here's a graph showing the total energy of the reactants. And if the reactants have more energy than the products, then the difference between the reactant and the products is the energy being released, and this is your exergonic reaction. Whereas over here, here's your reactants, and your products have a higher energy level, and so the difference between the products and the reactants is the energy input or energy needed to carry out this chemical reaction, then it's endergonic. So this is not spontaneous, energy is required, it's going to be ordered. So notice the reactants are tiny bits and pieces, and here we have formed nice little chemical bonds, so entropy decreases. Whereas over here, we have this nice product, this nice chain of molecule, and we're going to break it down into its pieces, so entropy increases, and this is going to be spontaneous. So I was going to say this would be cellular respiration, breaking sugar down into its parts. Let me make sure I type that in right. Yes, exergonic. And then this would be photosynthesis, taking CO2 and water and forming glucose and sunlight. So, yeah. Okay, now spontaneous chemical reactions. Go back, spontaneous. So over here, right? Cellular respiration. Do require activation energy. And the definition of activation energy is the energy needed to initiate that chemical reaction. So if you have a chemical reaction that has extremely high activation energy, that rate of that reaction is going to be really slow because fewer molecules will overcome that initial energy just spontaneously on its own. And so the rate of reactions can be increased, which means that we can increase the energy in reactant molecules as heat, or we can lower it by use of a catalyst. Okay, so with cellular respiration, we have glucose and oxygen, and we're going to break it down. It's going to be more random. We're going to release energy. Delta G this is exergonic, so it's a negative value, negative 686 kilocalorie per mole. Okay, so when you see a negative delta G, it's exergonic. Whereas with photosynthesis, it's the opposite. We're taking all that randomness and we're making it more ordered. Notice my delta G is positive. It's going to be endergonic. And notice that cellular respiration and photosynthesis are the opposites of each other. And so, here we are breaking bonds, okay? And here we're forming bonds, but it's the same amount of energy. It's just, positive versus negative. So how do enzymes work to lower activation energy? Well, first off, we need a catalyst. So catalysts are enzymes, okay, that can influence chemical bonds. So they influence chemical bonds by lowering net activation energy. Cool thing about catalysts is that they don't violate the laws of thermodynamics. They don't make reactions happen spontaneously. All they're doing is just lowering the activation energy. They're making the frequency of these molecules come in contact more frequent versus, not coming in contact with each other. All right, review question. An endergonic reaction has which of the following properties? So endergonic means that delta G will be positive, okay? And endergonic means that it's not spontaneous. We're forming orderly here, so B is your option. A spontaneous reaction is one in which what? The reactants have a higher free energy than the products. So it's A. What is activation energy? That would be D, the energy required to initiate a chemical reaction. Okay, 6.3, ATP, the energy currency of cells. Talk about the role of ATP in short-term energy storage and then distinguish which bonds in ATP are high energy. So ATP stands for adenosine triphosphate, and it is the chief currency that all cells use to carry out life processes that powers almost every energy requiring process that cells do. It's made up of 3 phosphate groups, a ribose sugar, and then an adenine nitrogen base. So the structure of ATP, there's my 5-carbon sugar ribose, and then we have adenine, and then the 3 chains of the phosphates. And just recognize that there are different forms of energy carriers that cells can use, but ATP is the chief one. When we get to glycolysis, we'll talk about GTP, PPI, PEP, and 1,3-bisphosphoglycerate. But how it stores energy, it lies in the triphosphate group. These phosphate groups have, I think, a negative charge, and so they want to repel and break away. And so this last bond right here is really, really unstable. So it's easy to break, and when you break this bond, you release energy. And then it becomes it goes from ATP to ADP. So this is adenosine triphosphate because it has 3 phosphates, and this is adenosine diphosphate because it has 2 phosphates. So ADP plus P plus the energy that you use to that formed, when that bond was broken. So when you cleave off the phosphate on the end, basically you have liberated this phosphate that temporarily binds to this intermediate molecule, but you just realize that it can go back to ATP. So ATP becomes ADP, ADP plus P can become ATP. So we call this hydrolysis. Here's my ATP molecule, and we can cleave off that last phosphate, and then we can form these two back together again, and that's why ATP is such a great short-term energy molecule. But it does drive endergonic reactions, so it does not proceed spontaneously. That means that the products, remember, have more free energy than the reactants. So energy released by ATP makes your delta G, your free energy, for coupled reactions more negative in this case. So here's ATP when we break it down, negative. When you form the bond, positive. ATP cycles continuously, so that it's that last triphosphate, or that phosphate in the triphosphate, is unstable. And so it's a horrible long-term energy storage, but it's a great short-term. ATP is cyclical. Like I said, it can be converted from one form to the other. And then really, you only have 50 grams of ATP in your entire body, which is a really, really small amount. So essentially, you only have a few seconds of supply of it. So your body is continuously making ATP from ADP plus P. Review questions. Where is the energy stored in the molecule of ATP? That would be D, the bonds connecting the two final phosphate groups. So that triphosphate. Why is ATP capable of driving endergonic reactions? And it would be B. I was about to say C, but then I said more positive. No, it's more negative. All right, 6.4 enzymes, biological catalysts. So discuss the specificity of enzymes, how enzymes bind to their substrates, and the factors that influence the rate of these enzymes' catalyzed reactions. So enzymes alter activation energy by lowering it, but enzymes, what they do is they work on substrates. So these molecules that bind to enzymes are called substrates, and they're very unique. You can think of enzymes as like locks and substrates as keys. They're very specific as to which enzymes work on. So enzymes lower that activation energy required to form new bonds. The reaction proceeds more quickly with the enzyme present than without. And the enzyme, the cool thing, is that it's not changed or consumed. And so we never see it in chemical reactions, like in the equations of it. And you only need a small amount of it since it is reusable. So, like I said, the enzymes and substrates that go together, they're very specific. And the reason for that is the sites on the enzymes that the substrates bind to are called active sites. So these are pockets or clefts where these substrates bind. They're very specific. They fit only to certain substrates. And when they do bind, we form this enzyme substrate complex. Then once it binds, a chemical reaction will occur, products are formed, and then those products will dissociate or fall away from that enzyme, leaving that enzyme to pick up another substrate and carry out the same chemical reaction. So a diagram to show this. Here we have my enzyme. These are the active sites that the substrate binds to. It binds to it. In this case, we're breaking this bond and forming brand new products that will dissociate or fall away from it. So here's the active site of the enzyme. Substrate binds to it. Once it forms, we get this enzyme substrate complex. And like I said, they're very, very specific. They only work with certain substrates. You can kind of see that this enzyme's only going to work with the two circles, and this one's only going to work with the square and this Tetris L-shaped piece. Now, enzymes occur in many forms. The multi-enzyme complex is basically an assembly line of several enzymes that work together. So like here we have an enzyme, and it'll cleave off a carbon and form CO2, and then it will pass it on to another enzyme that's going to use NAD plus to turn it into NADH. So the close proximity of these enzymes speeds the overall process of taking pyruvate, in this example, and form acetyl-CoA. So we call this, basically all it's saying is if you have a bunch of enzymes lined up in a row, then you have a multi-enzyme complex. So here's an example with pyruvate dehydrogenase complex found in your mitochondria, where we have one enzyme that does this process, and then it passes it on to the second enzyme, and it passes on to a third enzyme. So there are significant advantages with these multi-enzyme complexes is that, first off, your rate of enzyme reaction is going to increase the frequency of collisions with the enzyme and substrate. The substrate never leaves the complex, so it's never going to get lost, and you're never going to get these unwanted side reactions with it. And that all the reactions take place in that complex, and it can be controlled as a certain unit, so we can help better regulate it. Now, there are some non-protein enzymes out there, because I know a lot of times we say enzymes are proteins, but there are some enzymes that are non-proteins. RNA molecules called ribozymes can catalyze some chemical reactions. There are two types of ribozymes, intramolecular and intermolecular. You really don't need to know that, but really ribosomes themselves are considered a ribozyme. And if you remember our RNA world hypothesis, RNA has this ability to carry out chemical reactions, and RNA is a nucleic acid. It's not a protein. But some examples of non-protein coenzymes like vitamins as well as cofactors, minerals. Some factors that affect the enzyme function, there are 3 of them. Temperature. So some enzymes only work at an optimum temperature, so if it's above or below, it's not going to work as well, and the rate of the reaction is going to decrease. Okay. pH, same thing. Some enzymes work really well in a certain range, and if it's below or above that range, well then your chemical reaction is going to decrease. So we have a lot of enzymes that are sensitive to pH. This is just showing that pepsin's found in your stomach, so it works well in acidic concentrations. This is salivary amylase, an enzyme found in your saliva, so it's going to be around neutral. And then arginase, I'm not exactly sure where arginase is at. Okay, a third factor is inhibitors and activators. So enzyme activity is very sensitive to the presence of other substances that can bind to the enzyme and cause changes in shape. And so I'm going to talk a little bit about inhibition and activators. So here's my original reaction where you have an enzyme and a substrate and it binds. In this case, we're going to break it down into 2 products. But we have inhibitors that can bind to that same active site. And when they bind, they stay bound and they don't be released. And so the substrate can't bind to it because the active site's already occupied. So we call them inhibitors. A substance that binds to the enzyme, decreasing the activity. Very often, it's the end product of some type of biochemical pathway, and it can be used as a feedback inhibition. So I'm not saying it's always bad, but it can help us regulate chemical reactions. Now, there are 2 ways that enzyme inhibition can occur, and that is through competitive inhibitors and non-competitive inhibitors. So competitive inhibitors, compete with the substrate at the same active site. Non-competitive inhibitors bind to the enzyme in a different place than the active site. And as a result, the enzyme will undergo a shape change, so that way the active site changes and can't bind to the original substrate. So here's competitive inhibition, where it binds to the active site. Here's non-competitive. It binds to a different site on the enzyme, not the active site, and we have this shape conformation that undergoes, and the substrate can't latch onto it. See over here, this is like pinched inwards, and these are like open. Okay. So enzymes can exist in either active or interactive conformation, and we can call them allosteric enzymes. So allosteric sites are places where non-competitive inhibitors bind. Basically, they're the on and off switch. So if you have one that reduces enzymatic activity, we call it an allosteric inhibitor. And if you have one that increases or keeps the enzyme active, then we call it an allosteric activator. So here's allosteric. We'll start with activation. The activator binds to it. Notice that the active site's like all squished, right? But once the activator binds to it, it opens up, and now the it can bind to a substrate. Here is my inhibitor. The active site was active, but once the inhibitor binds to it, now it closes and gets shriveled up like this, and the substrate can't bind to it. We also have some cofactors, which just means that you need them in order to assist in the enzyme function. A lot of times they can be metal ions that do this, and I think we'll talk a few cofactors in cellular respiration. But here's an example of an enzyme with a cofactor. It could be a mineral or a vitamin, and this substrate can't bind to that site until the cofactor binds to it. That's all that's saying. So most enzymes need a cofactor to activate them, but without that cofactor, then the enzyme can't latch onto that substrate. So it says most vitamin deficiency diseases happen this way. Review question. Which of the following is not a property of a catalyst? It is B. Lowers the free energy. It does reduce activation energy. It does not change the result of it, and it can work in forward and reverse direction. So it's B. Which of the following statements is not true about enzymes? That would be C. Enzymes do not alter their shape in the process of reactions. Like they just do that, like just make products. What is the function of the active site of an enzyme? You're probably thinking A, but it's also B. So your real answer is D, both A and B. A multi-enzyme complex is capable of it's B, catalyzing a series of reactions using multiple different enzymes. What is the common factor that influences enzyme function at extreme temperatures and pH? Basically, it's asking why do enzymes malfunction when they're exposed to extreme temperatures and pH? And that is C. The shape of the enzyme changes. We mess up the levels of protein structure, either primary, secondary, tertiary, quaternary. So C. The discovery of ribozymes meant that C. Some RNAs have enzymatic activity. Final one, molecules that bind with the active site of an enzyme are, that would be B, competitive inhibitors, and allosteric inhibitors. Okay, final section here, 6.5 metabolism, the chemical description of cell function. So I'm going to talk about the different kinds of reactions. There's 2 of them. Discuss what is meant by metabolic pathway, and then recognize that metabolism is a product of evolution. So metabolism is the total of all chemical reactions carried out by an organism, and there's 2 types, anabolism and catabolism. Anabolism means that you are going to expend energy and make or transform chemical bonds. So you're going to take small molecules with energy and make a very large molecule. Catabolism is the reverse process of that. You're going to take a large molecule and break those bonds, and as a result, give off energy and make small molecules. So this would be like photosynthesis. This would be like cellular respiration. Now, the biochemical pathways are organized in chemical reactions in cells. So there are a lot of biochemical pathways that are in cells, and they occur in a certain sequence. And as a result, the product of one reaction becomes the substrate for another, kind of like that multi-enzyme complex. So there are many sequential enzymes, steps, in these biological pathways that take place in specific compartments inside of our cells. And that's why we have a lot of organelles that carry out specific jobs. So these biochemical pathways may have evolved in a stepwise fashion. So our earliest cells had to scavenge for energy-rich molecules from the environment. So they think, okay, well, life started in the ocean or in the water, kind of in this organic soup. And eventually they were going to use all the energy-rich molecules, and those become depleted, and the organism will need to evolve and find another molecule that's like a step before that molecule to make that original energy-rich molecule. So what I mean by that is, if H was this energy molecule that it used to use, but all of a sudden we run out of H, well, then it's going to need to find what can make H, what 2 molecules can make H. And so here we have F and G. So it says the first reaction where 2 energy-rich molecules F and G react to produce compound H and release energy. But then you're going to run out of F and G. So then you need a new reaction that can, you take E and it breaks down into F, or maybe it breaks down into F and G. So a new reaction is added as F becomes depleted, but it's made from another molecule, in this case, molecule E. But then you're going to run out of E, right? And so now you're going to be to D. So when E is depleted, the organism is going to make E from another precursor molecule, in this case, molecule D. And it just keeps going. Then you have C. But eventually, the final reactions of the pathway probably evolved first, and then we can go work ourselves backwards, right? So biochemical pathways evolve not at once, but maybe one step at a time backwards. Okay. Now, in order for biochemical pathways to be efficient, we probably had some feedback inhibition to help regulate it. it's, your cells don't always need to make a compound when there's plenty of it. So, you're just going to be wasting energy and raw materials. So it has to be regulated. And obviously this is going to be an advantage. You're just going to shut down production until the products are needed, and then you can jumpstart them up again. So the regulation often depends on the feedback mechanism where the end product binds to an allosteric site on the enzyme that catalyzes the first reaction. We call that feedback inhibition. Whereas as H increased, it would encounter all the allosteric sites on C and D enzyme and bind, shutting down the reaction and stopping the pathway. So, when you have a lot of H's, well, then maybe H affects this enzyme right here and shuts it down. And then when H decreases, well, then you don't have H affecting C and D. So as a result, C and D pick up again, and then D becomes E, and then E becomes F, and then you get H. And then when you have a whole bunch of H's, well, then H is going to go back and shut off this process again. So, yeah. Here's chapter 6.